I'll be talking about how to improve the sustainability of organic solvents. But before we start to address the question, we must first learn ourselves what organic solvents are. A formal definition of organic solvents is that they are carbon-based substances capable of dissolving or dispersing one or more other substances. But this is more of an abstract definition, right? And since you are not all chemists, let me offer a more practical example. Let's say that you're a pharmaceutical scientist and you want to make off the shelf paracetamol. And this requires the combination of compound A and B stated to the left. This is called the chemical reaction. However, these types of reactions don't just occur. And by dissolving both compounds in an organic solvent in the middle, you facilitate the reaction. This is because solvation allows for molecules to rapidly move around, eventually striking each other with enough energy for the transformation to occur. Wherever a chemical reaction is required to produce a chemical product, you can find organic solvents. And this is why you find the use of organic solvents in a ubiquitous range of industries. And here's a chart detailing the uses in various industries. I'll leave it up here for a few seconds for you to observe. Since organic solvents are the bulk medium in which chemical reactions occur, they account for around 80 to 90% of the mass of the chemical processes. However, when the reaction is complete, the solvent is actually not desired, and the final step of chemical processes almost always involves the separation of the final desired product from the organic solvent. And this kind of explains the large amount of organic solvent that is wasted at the end. Because organic solvents account for such a big part of chemical processes as well as the waste generated from it, they receive a significant amount of attention from a sustainability perspective. Here are 8 different classes of organic solvents and individual compounds which belong to those classes. The keen-eyed amongst you may have already noticed the similarities between the solvents which belong to the same class. If you have already done so, you can call yourself a chemist. Organic solvents with different chemical structures have varying physical-chemical properties, and an effective solvent choice can improve the efficiency of a specific chemical process. However, I became curious of the relevances of these classes on the sustainability of organic solvents. Would solvents of the same class be similarly sustainable? To answer this question, the following plot was constructed. On the vertical axis is the environmental, safety, and health indicator for organic chemicals. And on the horizontal axis is the LCA value for the energy consumed by a particular solvent throughout its life cycle. A key to help you interpret this chart is that sustainability increases as you approach the origin. An attempt was made to spatially correlate the solvents belonging to the similar classes. However, there were no apparent relationships. So the answer to my question was a big no. However, this still does mean something. Since no particular class of organic solvent is more sustainable than another, this allows for specific solvents with low sustainability to be substituted with a different solvent of the same class which has similar properties. In not all but many cases, this might not significantly affect the efficiency of the chemical process. The key takeaway here is that when designing chemical processes, we should use the most sustainable solvent from a particular class. Then what about for the management of waste of organic solvents? This is also a very relevant question since so much solvent waste is generated. The two primary schemes of organic waste treatment is incineration and distillation. The two has its own pros and cons. Incineration involves the burning of organic solvents. Some positive energy output is released in this process, but this comes along with various pollutants such as VOCs, NO2, CO2, and etc. This is also the more economic option since you don't require a specific facility. Distillation is the other option. This option allows for the recovery of solvents by evaporating them and collecting the condensation. This is an environmentally friendly option since you get the solvent back, but it requires high energy input and a dedicated facility. Cumulative energy demand, or CED, is the life cycle assessment metric used to gauge the sustainability of each process. And a low value for this indicator means that the process is more sustainable. The following graph plots the distillation over incineration for the cumulative energy demand. What this means is that a value larger than 1 signifies that distillation is more energy demanding, and a value lower than 1 signifies that incineration is more energy demanding. In most cases, it seems like distillation is more energy efficient than incineration, thus being more sustainable. This is likely because you can reuse the solvent that you get through distillation instead of producing it again. In the case of treatment schemes, a rough correlation amongst classes could actually be observed. For example, incineration seems to be more energy efficient for all aliphatic hydrocarbons, which are denoted in black. Alcohols, which are denoted in blue, also seem to lean slightly towards incineration as well. The key takeaway here is that classes play some role in determining what the most sustainable waste management scheme is for organic solvents. Thank you, and here are the references.